So the very existence of solids and liquids, of course, is a very important manifestation of intermolecular forces, but there are other things that occur because of intermolecular forces. The ones we're going to talk about are surface tension, viscosity, and capillary action. And this picture of a spider web with little drops of dew on it, that's an illustration of surface tension. And this is a paper clip floating on top of water. And that shouldn't happen, right? Because a paper clip is made out of metal, and metal is more dense than water, and so it should sink. And normally it does, but if you have pure water and are very careful, you can get a paper clip to float on the water. It's very similar to the little bugs that skate on top of the water. Have you seen those? Or water skaters? You can see in this this photograph that it almost looks like there's a skin on top of the water, and the paper clip is kind of wanting to go down. It's a lot like you could imagine there's a pool cover, and then you flop down on the pool cover, right? And you're going to kind of sink down a little bit, but you're not going to break through the pool cover, right? Because it's strong enough to hold you. So that's sort of what's happening with the paper clip there. Anybody like to fly fish? My husband loves to fly fish. He ties flies. It's really cool. He's got fur and feathers all over the place. Why does this fly float on the water? Yeah, it's not very heavy, but it's more dense than water. If you put it underwater and get it all wet, it will sink to the bottom. But if you just lightly plop it onto the surface, it'll float because of the surface tension of the water. Surface tension is a tendency of liquids to minimize their surface area. It can be quantified. It would be the energy required to increase the surface area by a certain unit amount. So 1 unit would be millijoules per square meter. That's the surface tension of water, 72.8 millijoules per square meter. So to increase the surface area by a square meter would require 72.8 millijoules of energy. Great, we don't really need to know about that. In order for this trout fly to sink, to go into the water surface area is going to have to get larger because you have to make a pocket for the thing to sink into it. That requires energy. If we think of these as water molecules, like just a two-dimensional slice of water molecules, we've got intermolecular forces holding the water molecules together, right? The interior molecules are going to have forces on all sides. They're all attracted to each other. They're all great. I'm like surrounded by all my friends. The ones on the surface are attracted to those next to themselves along the surface and to the ones on the interior, but they don't have any neighbors on the outside above the surface, right? So these guys are not as happy. They don't have as much attraction. So if we make a larger surface area, then we have more of the molecules with fewer attractions. And that is not a more stable situation. Okay, that's going to be higher in energy than when we have more attractions. So these molecules in the interior have lower energy than the ones on the surface. And it wants to minimize the energy, lower energy, and so we want as many molecules as possible to be on the inside. So water will form a sphere, a droplet, because a sphere is a shape with the smallest amount of surface area for its volume. In order to increase the surface area, we're going to have some of these interior molecules move to the surface, and they don't want to do that. Any questions? So surface tension is going to depend on the strength of the intermolecular forces. If you have weak intermolecular forces, you'll have less surface tension. If you have strong intermolecular forces, you'll have greater surface tension. Surface tension is why small droplets of water are spherical. You can see that on this spider web, little teeny tiny spheres of water. They form those little beads of water because that's the way in which they can have the smallest amount of surface area, have the most molecules being in the center. When we see larger drops, like if you watch a dripping faucet, you would see sort of a teardrop shape, right? It's very, very bad. Why isn't it a sphere? Because gravity is pulling on it. The reason it hangs there at all is due to surface tension, but the gravity is pulling on it, and so that distorts the sphere. Here, this is actually that same astronaut. Here he's looking at a big drop of water on the space station, and it's going to be perfectly symmetrical, perfectly spherical, because there's no gravity affecting it. Viscosity is the resistance of a liquid to flow. So you can think of it as being thick, right? It doesn't want to flow very well. So it makes me think of maple syrup. Motor oil is thick. Honey is thick. It doesn't pour easily. Whereas water pours much more easily than honey does, right? Honey is more viscous. And of course, this can also be quantified. The units would be a poise, which is a gram per centimeter second. So you've been told that, you can forget about it now. If we have stronger intermolecular forces, we have greater viscosity. Just think about it. When you're trying to pour a liquid, what has to happen? The particles have to slide past each other, right? And move and pour out. So if they're very slippery, they'll pour easily. If they're very sticky to each other, they'll pour more slowly. So they'll be more viscous. So we see viscosity increases with molar mass. Here are those hydrocarbons. And as we go higher and higher molar mass, we're going to have larger dispersion forces, and we're also going to have longer molecules, so we've got more surface area for those dispersion forces to stick, and we see that the viscosity increases. So viscosity depends on the strength of the intermolecular forces. It also depends on molecular shape. Longer molecules have larger surface area to stick to each other, and they can also sometimes get tangled up with each other. Viscosity is going to depend on temperature. At a higher temperature, the particles have more energy, and so they're sliding more easily. Viscosity is lower at high temperatures. Viscosity is higher at low temperatures. And if you think about, say, pancake syrup, right? If you keep it in the refrigerator, it's going to be really, really thick. Right? If it's at room temperature, it's kind of thick. If you heat it up in the microwave, it's going to get very runny, right? Higher temperature, lower viscosity. So motor oil, the function of motor oil is to coat the moving parts of the engine of your car and help them to slide past each other so they don't wear out. So you need just the right viscosity for your motor oil, because if it's like water, it's just going to fall down to the bottom and it's not going to coat the surfaces correctly. If it's too viscous, though, it's like throwing peanut butter in there or something, it's not going to do its purpose of lubricating. So one of the tricky things about motor oil is, okay, so when you start your car, the engine is room temperature or outside temperature, could be really cold. But once you get the engine running, it's going to get hot. So that's going to cause the viscosity of the oil to change. The new motor oils have polymers in them, and these polymers are so cool. At low temperatures, the polymers coil up, and so they make more globular shapes, which reduces the surface area for them to interact, right? So that would reduce the viscosity. As they heat up, they unwind and become long and tangly, which causes the strength of their intermolecular forces to increase and causes the viscosity to increase. So these polymers can be used to moderate the temperature effects of viscosity in motor oils. Very, very neat. Any questions? I can never remember exactly how this all works, but this 10W40 is talking about the viscosity and different temperatures. That's not just some random number. Capillary action is also due to intermolecular forces. Here we've got a patient, a finger prick to draw some blood, and the technician takes this capillary tube and just touches it to the blood, and the blood just runs up the tube. There's no suction or anything. It just does this all by itself. That's called capillary action. The ability of a liquid to flow against gravity up a narrow tube. There's two forces at work here. There are cohesive forces and adhesive forces. So cohesive forces are the forces of attraction between the molecules in the liquid. Those are the intermolecular forces that we've been talking about between the molecules of the liquid. Adhesive forces are attractive forces between the liquid and the tube. So what happens is the liquid is attracted to the tube, and so it begins to crawl up. But it's also attracted to its fellow liquid molecules, and so it's going to drag the rest of them up. In a small tube, you have less, how do we explain it? You've got more contact with the tube and less molecules in the middle that need to be dragged up. And so the smaller the diameter of the tube, the higher the liquid will crawl. So this over here, it doesn't crawl up very much at all, but this little teeny tiny one, it goes very high. If you had weaker intermolecular forces, that would affect the capillary action. But again, it's a balance between the forces of attraction for the molecules to each other and the force of their attraction to the surface of the tube. So depending on what the tube is made of, that can affect the capillary action as well. We've talked about the meniscus, especially in lab. We learned that you're supposed to read the bottom of the meniscus. So here we see this meniscus. It almost looks like there's a contact lens floating on the surface of the water. It's curved, right? And that is also due to a type of capillary action, right? It's trying to crawl up, but it just can't. So it's climbing up the edges. Those are the adhesive forces, and the cohesive forces are keeping this part together. So here we have stronger adhesive forces than cohesive forces. Here, this is liquid mercury in a glass test tube. It also has a meniscus, but its meniscus goes the opposite direction. It bulges up instead of down, because here the cohesive forces are stronger than the adhesive forces. Some types of plastic, with water, you'll see no meniscus. It'll just be flat. And that's because you've got a balance then between the adhesive and cohesive forces.